In this video, we're going to look at general curvilinear motion. So far, we've looked at motion along the line just in one dimension. So we're just moving like along the line. Now we're going to do 2D and 3D motion. And so that's what we're going to consider in this video. And again, in the following sections, we'll use, of course, remember velocity is the SDT, or velocity depend on the context, could be dx/dt. And acceleration, of course, is dv/dt, which is equal to the second derivative of ds/dt, like that. Now, we'll have to remember implicit differentiation. And look at the video below if you've forgotten. Let me just do a real basic implicit differentiation now. So suppose we have y equal 4 x cubed. And let's say y is a function of t. So let's find dy dx dy dt, and the second derivative of y with respect to t. So, of course, if we're looking just for dy dx, we just do our normal differentiation. So that's going to be just dy dx equals 12x squared, like that. That's what we're most used to. Now, if though we're treating, let's say, y and x are functions of t, so we want to find dy dt, remember we have to go back to implicit differentiation. So dy dt, again, starting back up here, remember we have to use like the chain rule. So this would be 12x squared. But remember, we're assuming when we do this that x is a function of t. So there's a function of t buried in here. So we have to take the derivative of that, but we don't know what that function is. So we just have to use dx dt. Now, again, usually we're going to call dx dt equals to x dot. So, and then, of course, the second derivative is going to be x double dot. And the same thing with y. So when we did this over here, we took the derivative of this with respect to t. On the left-hand side, we could have called that y dot. And the right-hand side, we'd have 12x squared, then times the derivative of what's here would be x dot, like that. And finally, let me do the last one. We want to find the second derivative with respect to t. And so we're going to start with what we have here, which is, so we have this, we'll take the second derivative. And over here then, we have a product, so we'll take the derivative of the first times the second. And of course, when we take the derivative first, we're going to bring this down here, be 24x times x. But then we have to take the derivative of this. We don't know what that function is with respect to t. So we'll just call that x dot. So that's the derivative of the first times the second. Plus the first times the derivative of the second, like this. And let me move that up so it's a little bit clearer, sort of shiny. So we have that. So be sure, again, look at the video implicit differentiation if this, if you don't remember a lot of this stuff. Again, you could go one more step here and just call this 24x dot squared plus 12x squared x double dot. So we'll take a look at some problems. So we're going to take a look at this problem 12-71. A particle originally at rest and located at 0.325 is subject to acceleration of 6ti plus 12t squared k feet per second squared. Determine the particle's position at time equal 1 second. We're going to take a look at this. So we're going to take a look at this problem. So we're given the acceleration, and since we're starting at time 0, and the velocity is 0, we don't really have to mess too much with the bounds. In other words, because we're going to have like dv from 0 to v, and over here we'll have time 0 to time t of our acceleration. So over here, when we integrate this, we're just going to get v. And so we're going to have to integrate this over here. The one thing to keep in mind, when we integrate 0, and our initial condition is 0, we're going to get nothing. We remember, whenever you have something like this, whenever you're integrating 0 and you have bounds, this will end up just being 0 again. So again, on the right-hand side, we're going to integrate 6ti plus 0j plus 12t squared k dt. And so just integrate each individual term. So if we integrate this, we'll get 3t squared. And like I said, when we integrate this one, because we have bounds, whenever you integrate 0, and if you have bounds on your integral, this will just stay 0. And over here, this will be what? 4t cubed k. And again, it's going to go from 0 to t. And so we're just going to replace t with t, and the lower bound is 0. So we can even just skip that step because we're going to end up with the same thing. And then when we want to find S, now this time we have to be a little bit careful because we're not starting at 0. We're not starting at position 0. We're starting at position, we were given the position of what was that, 3I plus 2J plus 5K. That was our initial starting position. So that's going to be our lower bound. Then our upper bound will be S over here. And then this is just the vector S. So this time we'll have to have something on the bounds on the left-hand side because we're not starting at point 0. So once again, we'll integrate each term, 0 to t. And we're going to integrate this. Remember, the integral of velocity will give us position. So we'll put velocity in here. Like this, and then we'll integrate that. And on the left-hand side, see, we'll have an S, and our lower bound will be 3I plus 2J plus 5K up to S like this. Right-hand side, we'll integrate this, we'll get what? T cubed I. And once again, when we integrate 0 and we have bounds, that's just going to stay 0. Integrate this. This is T to the 4th. And again, it'll go from 0 to T, but when we plug it in, we'll still get this. Let me just show it just in case. So over here, then down here, and we put our bounds in, we'll get S. Then the lower bound will be minus 3I plus 2J plus 5K. And then on the right-hand side, we're going to have T cubed I plus 0J plus C. I forgot a K up here. Please fix that. K, like this. Please fix that K right there. And then finally, if we want an equation for S, we'll bring all these terms over the right-hand side. And we'll have T cubed. So the 3I will become a positive 3I and add to this. And then this 2J, which is negative over here, become a positive. And then the 5 will add to the 5 over here. Like this. So finally, we want to find what the position is when t is equal to 1. And so we want to just plug in t. It's going to be plug in 1 in here. So we put 1 here. 1 cubed is 1. This would be 4. This will still say 2. 1 to the 4th is 1. This would be 6. Four plus 2 plus 6 for the point. This. So again, just to review the way we handled that, we were given a vector form of the acceleration. We just integrated the components. And again, if we have bounds we don't, if we have bounds, integrating 0 always will just give us 0. And in some cases, if the initial condition is 0, we can actually sort of skip some steps here. Like here, I just went ahead and put the t in to start with. We didn't really have to substitute. Same thing here. Next, we're going to take a look at this problem here. A rocket is fired from rest at x equals 0 and travels along a parabolic trajectory described by y squared is equal to 120,000 x meters. If the x component acceleration is given by 1/4 t squared, meters per second squared, where t is in seconds, determine the magnitude of the rocket's velocity acceleration when t is 10 seconds. So let's take a look at this. So let's take a look at the situation. Rocket fired from rest at x equals 0. And the relationship between x and y is given by this. Now we know the acceleration of x in the x direction, and we want to find the velocity and acceleration when t is 10 seconds. So we're going to need to find the velocity. Now, of course, we're going to need to find both the x and the y components of velocity. So might want to keep that in mind. Need like, a of y, acceleration in the y direction, velocity in the y direction. We have a of x, and we also need v of x. And of course, what this would mean is that we need, this is the same as needing y double dot, which that's the acceleration in the y direction. And we need y dot, and we need x dot. And of course, this is the same as dy dt squared, and this is dy dt, this is dx dt. So that's what we need. And so probably the best strategy would be to find the values, maybe find out what the equation for x is. So let's do that. So strategy. Find equation for x. We want x equals something. And then substitute it into this. And put it in there. And so that's what we're gonna try to do. So we'll start with this and integrate, because we want to eventually find x. So we now need to find the velocity in the x direction, so we can integrate this to find that. We'll integrate ax dt to find the velocity, and the initial velocity is 0, initial time 0. So we can almost ignore these bounds. We really don't have to substitute anything, because it's just going to end up with t's over here. So this is going to be v of x. Then when you put the bounds in, it'll still be v of x. So I'm going to just skip that step. And so we're going to integrate this over here, 0 to t. This would be like 1/4 t squared dt. And And we integrate this, we'll get 3 here, so that'll be, and divide by 3, 0 to t. So notice when it's 0 to t, we're just going to end up putting t back in, and the lower bound is 0. So I'm going to just ignore that. And we just have this. And once again, if we want to find x, we're going to integrate 0. Again, since we're starting at x equals 0, once again, the bounds really aren't going to be relevant again. And so we're going to integrate the velocity. So it's going to be 0 to t 1/12 t cubed dt. And we do this, we're going to get x on the left, and we'll put in x and 0, still be x left with x, and divide this by 4, 1/48. Like this. So that gives us an equation for x, and we can then substitute into our y equation. And that's going to give us y squared is equal to 120,000. And then for the x, we're going to put this in. And if we divide this out, it comes out kind of nicely. This is going to be 2,500 t to the 4th, like this. And so now we're going to need to know the velocity. And so, like I said before, we need to know y dot. So take the derivative of this. And again, we're taking the derivative with respect to t to get y dot. So the right-hand side will be just like the usual derivative. The left-hand side we'll have to do implicitly. So again, do the chain rule. So we have 2y. But then we have to take the derivative. Remember, whenever we use a chain rule, we have to take the derivative of whatever's in here. But we don't know what that function of t is. That's why we put the y dot here. And then on the right-hand side, we take the derivative over there. We're going to get like 10,000 t cubed, like that. So we're also, remember, we're going to also need y double dot. So let's take one more derivative. And so remember, over here we have a product. So derivative of the first times the second. So it took the derivative of the first times the second plus the first times the derivative of the second, like that. And the right-hand side is just going to be, what is that? 30,000. T squared. So we have these two equations. And actually, we're going to need this equation as well. So we want to find what's happening when t is equal to 10. So first, let's find out the y values when t is equal to 10. So we can just substitute into these. We can just use equation 1, equation 2, equation 3. So when t is 10 seconds, if we use equation 1, we can just plug stuff in. I guess that's equation 1 right there. We're going to get y squared is 2,500 times 10 to the 4th. And this gives us like 25 million. And then we take the square root of that. When we take the square root, we're going to end up with 5,000 at the y component when t is 10. Then we're going to also need the velocity. And again, at 10 seconds, we'll put that in here. So we're going to use 2y, y prime, 10 cubed here. And then we're going to need our y here from the previous step. Y dot. And cubed like this. And when you put this all in your calculator, you get 1,000. And what were these? We were in meters. Meters per second. Actually, we had meters up here, like this. And then we can use our equation 3 to find our acceleration in the y direction. Use this up here to y double dot plus y double dot is 30 t squared. And then let's just substitute everything in. We had this from up here. Of course, we can just write this as squared here. Plus 2 y is 5,000. Y double dot. And 10 squared here. And of course, this is 2 times 10 to the 6. And this is 10,000. And then on the right-hand side, we have 3 times 10 to the 6. So we could actually subtract this from this, and that looks like that's just going to be 1 times 10 to the 6. Then y double dot is going to be 100. meters per second squared. So we have our y position, we have our velocity in the y direction, we have our acceleration in the y direction. Now we probably going to need our same things in the x direction. And we're going to have to use these equations here. Again, let me just use this equation right here. And we have our x. Of course, we were given our acceleration. So let's use those. So x, so again, when t is 10 seconds, x is going to be equal to 148 10 to the 4th. I'm not even sure if we're going to need this this position or not. To 8.33. And then our velocity was in the x direction was given over here. And we can just call that x dot if you want. 1/12 t cubed. And at t equal 10 seconds, it's going to be 10 cubed. We divide that by 12, we get 83.33. And up here, this was meters per second. Then finally, x double dot, that was our original acceleration that we were given. And that's going to be our 1/4 t squared, 1/4 at 10 squared. That's going to be 100 divided by 4. So I guess that's just 25 meters per second squared, like that. Finally, our velocity is going to be given by velocity in the x direction squared, y direction squared. And of course, this is just x dot and y dot. And we just found those to be x dot here was 83.33 squared. Y dot, we found that a minute ago. And that was 1,000. And when we calculate that, we get like 1,003.5. And then the acceleration is going to be square root of the sum of the squares of the x and y acceleration. So for the x, we had 25. For y, we had 100. And when we put those together, we put that in the calculator, get 103.1. Meters per second squared. And next, we're going to take a look at this problem. And first thing, notice that there is a typo in your book, at least in the version of the book that I have. the equation at the bottom here, notice it should be x squared over 4 plus y squared equal 1. And I think the original had like a v squared instead of a y squared. So it should be x squared over 4 plus y squared equal 1. So please fix that. And so we have this mechanism. It's moving to the right at 10 meters per second. And pegs A and B are restricted to move in the elliptical slots due to the motion of the slotted link. If the link moves with a constant speed of 10 meters per second, determine the magnitude of the velocity and acceleration of the peg when x equal 1 meter. So this looks like an interesting problem. So we're basically given this equation, this x squared over 4 plus y squared equal 1. That gives you kind of the equation of the slot. That's kind of showing you what the relationship between x and y is along that slot. So we're given this equation, and we're going to want to take implicit derivatives of this. But let's first write down what we know. Notice that the mechanism is moving to the right at 10 meters per second. So again, it moves horizontally. It moves horizontally at 10 meters per second. Of course, what does that mean? That means the x component is changing at 10 meters per second, and it's going to the right, so it'd be a positive position. So we know that x dot is going to be 10. So we have something that we can start with. And so let's go ahead and take implicit derivatives. So let's just go across and take derivatives. Again, this is going to be 2 divided by 4. So when we take the derivative of this, we're going to end up with x and 2 over 4, which is just going to leave us with 2. But remember, we're assuming this is a function of t, so we have to take the derivative of this, and that would be x dot. Like that. And then same thing over here. This is going to be 2y. Then times the derivative of this, because it's some function of t that we don't know. So that's to be y dot. And on the right-hand side, the derivative of the constant is going to be 0. Again, we'll call this equation 1 because we're going to refer to that. Take another derivative. And now we have a product here. So the derivative of the first is going to be x dot over 2 times the second plus the first times the derivative of the second, like that. And of course, we can write that as x dot squared. And then over here, derivative of the first times the second plus the first times the derivative of the second. Like I say, we can write these. This is x dot squared over 2 plus x double dot over 2. And we can write this as y dot squared plus 2y, y double dot is 0, like this. now we need to find information when x equal 1. So find y when x equal 1. So we can just use our original equation. Let me sort of name these. Let me call this original one equation 0. I called this one equation 1. Let me call this one equation 2. So use equation 1. Excuse me, equation 0. And so plug x equal 1 in here. Equal 1 like this. And then if we bring this to the other side, that's going to be 3 divided by 4. Then we take the square root of that, we'll get y equals the square root of 3 over 4, which is going to be the square root of 3 over 2. Now, again, remember when you take the square root, you'll get a plus and a minus, but we can avoid the, we can ignore the negative one. We can just do we just consider the positive one here. So we'll just ignore the negative one because that will be in the negative direction before the beginning. So we don't care about that case. So now to find y dot, we can use this equation right here to find y dot because we know x dot, and we want to find y dot. So now to find y dot, use equation 1. So that'll be this up here. Let me put this up here so we can see a little bit better. And so again, we want to find that when x is 1, so this will be 1 here over 2. And we know x dot is 10. And plus 2 times y, we found that y was square root of 3 over 2. And y dot equals 0. And so this is going to be 5. Let's see, these are going to cancel. So let me just go one more step here. This will be 5 plus square root of 3. Y dot is 0. So you can see y dot is going to be negative 5 divided by the square root of 3. And when you put that in your calculator, that's going to be minus 2.88 meters per second, like that. And finally, we need to find the y double dot. And for y double dot, we'll use this equation here, equation 2. And so just start plugging stuff in here. Once again, x dot, using this up here, x dot is going to be, it was given as 10 squared divided by 2 plus x Remember, we're finding this when x is equal to 1. Now, one thing to remember, I should have noted this before, our velocity horizontally was 0. Was 10, and it was constant. So this is going to be 0. So, or the acceleration is 0 in the x direction because we had a constant velocity. And then divide that, we can, of course, that's still going to be 0. Then go over here to y dot squared. And we found y dot up here minus 2.88 squared plus 2y. And we found y a minute ago to be square root of 3 over 2. And that's times 2. We put that in here. And then times y double dot, that's what we were trying to find. That. And let me push this up. Sorry about that. So I plugged the rest of the things into equation 2. So we had 10 squared over 2, 0, 2, negative 2.88 squared, 2 times square root of 3 over 2 times y double dot. And when you put this all in your calculator, so this is going to be 0. This is going to be 50. Do this and bring over everything to the right-hand side. And this is going to be negative 38.44 meters per second squared. So finally, to find the acceleration, that's going to be, the velocity in the x direction, which is x, excuse me, the acceleration in the x direction, acceleration in the y direction, but it's constant in the x direction. The y, we have this, we're actually going to end up with also 38.44 meters per second squared. So the main thing is when you approach a problem like this, see what we have originally. And something, again, I should have written at the beginning here, it moves horizontally at 10 meters per second, and this was constant. And so that means that our acceleration next direction is going to be 0. That's why when we got down to this step here, we could put that the constant velocity, so the acceleration was 0 in x direction. Interestingly, though, even though acceleration in x direction was 0, in the y direction it was not 0.